Electromagnetic effect, the effect in which the pi electrons are shifted either toward or away from the attacking species is called electromagnetic effect. Characteristics of electromagnetic effect: it is temporary effect and can be reversed back. It takes place only in the presence of the attacking species, nucleophile or electrophile. It is written by E. It is shown by the curved full-headed arrow. This effect may reinforce inductive effect or may oppose this, but when two effects oppose each other, another electromagnetic effect dominates over the inductive effect. Type of electromagnetic effect: positive electromagnetic effect, negative electromagnetic effect. Positive electromagnetic effect, the effect in which the pi electrons are shifted toward the attacking species is called plus E effect. In the plus E effect, the attacking species is an electrophile. Negative isoelectromagnetic effect, the effect in which the pi electrons are shifted away from the attacking species is called minus E effect. The minus E effect, in this effect, the attacking species is a nucleophile. Difference between inductive effect and electromagnetic effect. Inductive effect, the effect in which the dispersal of sigma electrons take place either toward the electron withdrawing group or away from the electron releasing group along the carbon atom chain is called inductive effect. It is permanent effect. It involves the displacement of sigma electrons. It involves the partial separation of the charges. No ions are formed during this process. Presence of multiple bond is not necessary. It takes place in the absence of attacking species. The electron of bond pair are slightly displaced toward more electronegative and they do not leave their molecular orbital. Electromagnetic effect, the effect in which the pi electrons are shifted either toward or away from the attacking species is called electromagnetic effect. It is temporary effect. It involves the shifting of pi electrons. It involves the complete separation of the charges. Ions are formed during this process. Presence of multiple bond is necessary. It takes place in presence of attacking species. The bond pair electrons leave their original orbitals. Resonance or mesomerism, the process in which one molecule is represented by more than one structure is called resonance or mesomerism. Resonating structure, the different structures formed during the process of resonance are called resonating structures or canonical structures. Resonance hybrid, the structure in between the different resonating structures is called resonant hybrid. The circle in the benzene ring represents the movement of pi electrons. The different resonating structure given by Dewar are: the Dewar structure are less stable than other resonating structure because Dewar structure has no cyclic conjugation need of resonance. There are some molecules whose all the properties cannot be explained with the help of single structure, so we have the need to take the help of more than one structure to explain all their properties, that is resonance take place. Condition for the resonance or characteristics: the molecular should be planar, that is, the central atom should have the sp2 hybridization. The molecular should have the double bond or single bond in alternate position. The atom having positive charge or free radical or negative charge or the lone pair electrons is attached by single bond to that atom which further have the multiple bond. In the resonance, pi electron or lone pair electron are sometimes the sigma electrons of the alkyl groups are involved. The different resonating structures differs only in the position of the electron pair. The number of paired and unpaired electrons in each structure must be the same. The position of the nuclei of each atom in each of the contribution structure must be the same. Equivalent contributing structure are of equal energy, and thus the contribution to the resonance hybrid structure will be the same. Type of resonance: minus R effect, plus R effect, plus minus R effect. The effect in which the central atom of a group having positive charges decreases the electron density from multiple bond, that is ortho-para position of the benzene ring present in the conjugation to it is called minus R effect. The minus R effect group should have the positive charge or multiple bond. The minus R effect group are NO2, CHO, COR, COOH, COOR, CN, SO3H, etc. The minus R effect group present on benzene ring decreases the electron density from ortho and para positions, so the electron density will be more at the meta position, and thus the incoming electrophile will attack on the meta position. Hence, the minus R effect group are also called meta directing group. In other words, the minus R effect group direct the incoming electrophile toward the meta position. The effect in which the central atom of a group having free radical negative charge increases the electron density toward multiple bond, that is ortho-para position of the benzene ring present in the conjugation to it is called plus R effect. The plus R effect group should have negative charge or lone pairs. Example: the plus R effect group are OCH3, CH3, NH2, OHCl, etc. The plus R effect group present on benzene ring increases the electron density at the ortho-para position, and thus incoming electrophile will attack at ortho-para position. Hence, the plus R effect group are also called as ortho or para group. In other words, the plus R effect group direct the incoming electrophile toward the ortho-para position. Hyperconjugation or no bond resonance or Baker-Nathan effect. The process which takes place when a sp2 hybridized carbon atom is attached to the sp2 hybridized carbon atom which contain at least one H atom is called hyperconjugation. During this process, the unhybridized orbital of the sp2 hybridized carbon atom overlap with the filled orbital of sp3 hybridized carbon atom. It is to be noted that more the number of hyperconjugated system, more will be the stability, and then number of hyperconjugated structure formed will depend upon on the number of H atom attached to the sp3 hybridized carbon atom. The hyperconjugation is also called no bond resonance because in the different hyperconjugated structure there is one of the H bond which formed no bond with carbon atom. The hyperconjugation is also called Baker-Nathan effect because it is given by Baker and Nathan. Aromaticity: the compound which resemble benzene in their chemical behavior and distinguish them from aliphatic or alicyclic compound are called aromatic compound. Characteristic or properties of aromatic compound. The properties of aromatic compound are: first one, they have high degree of unsaturation which is suggested by their molecular formula. They have a conjugate system of double bond, so they are resistant to addition and oxidation reaction. Instead, they prefer to undergo electrophilic substitution reaction like halogenation, nitration, sulfonation, etc. They have high thermodynamic stability, which is shown by their low heat of hydrogenation and combustion. Their molecules are generally 5, 6, or 7 membered ring compound. Their molecules are flat as shown by X-ray and electron diffraction method. Theory about aromaticity. Many theories have been put forward to explain about aromaticity, and these are: first one is resonance theory. This theory was given by M.J.S. Dever. According to this theory, in aromatic compound, all the atoms take part in a single conjugate system and have high resonance energies. Example: benzene, naphthalene, anthracene, and penthrene have high resonance energy and hence are aromatic. Limitation of resonance theory. It cannot explain the aromatic character completely by itself. Example: heptafulvene has the same resonance energy as that of benzene, but behave only as a typical polyene and not as an aromatic compound. Second theory, aromatic sextet theory. This theory was given by Robinson and Hermite in 1925. According to this theory, the aromatic compound will contain a closed loop of 6 electrons. Due to the presence of closed loop of 6 electrons, this theory was called aromatic sextet theory. Example: each carbon atom in benzene contribute 1 electron and 6 electrons form a closed loop, and it is this closed loop which is responsible for its stability and aromatic character. Example: like benzene, pyridine has a closed loop of 6 electrons. In this compound, each of the 5 carbon atom and 1 nitrogen contribute 1 electron each toward the aromatic sextet formation. However, in 5-membered heterocycles like furan, thiophene, and pyrrole, each of the 4 carbon atom contribute 1 electron while the heteroatom OSN contributes 2 electrons toward the aromatic sextet formation. Limitation of aromatic sextet theory. It could not explain the aromatic character of compound containing 2, 10, 14, 18 pi electrons. Third, Huckel rule. It is important rule, and this is given by Erich Huckel, a German physicist, in 1931 on the basis of molecular orbital calculation. According to this rule, any compound will be aromatic and stable if it fulfill the following criteria. First one, the molecule or ion must be flat, planar, or nearly so. The molecule should have cyclic cloud of delocalization of pi electron above and below the plane. The pi electron cloud should encompass all the carbon atom of the cyclic system. The molecule or ion should have total number of 4 n plus 2 pi electrons, where n is equal to 0, 1, 2, 3, and etc. These criteria are collectively known as 4n plus 2 rule or simply Huckel rule. In other words, it can be stated as monocyclic, polycyclic, planar, completely conjugated polyenes containing 4n plus 2 pi electron and having a cyclic pi electron cloud encompassing all the carbon atom in the ring are aromatic in nature. A molecule which does not satisfy any one of more of the above condition is said to be non-aromatic. Application or validity of Huckel rule. According to Huckel rule, aromatic compound need not necessarily contain a benzene ring, but the molecule of the compound must be planar and should contain cyclic compound of delocalized 4n plus 2 pi electron above and below the plane of the ring. 2 pi electron system. In cyclopropene, 2 pi electrons are not completely delocalized over all the 3 carbon atoms of the ring. So cyclopropene is not aromatic. On the other hand, in cyclopropenyl cation, the 2 pi electrons are completely delocalized, so it should be aromatic. This has actually been found to be so. In fact, cyclopropenyl cation is quite stable, and the salt of a number of cyclopropenyl cation, such as triphenyl cyclopropenyl cation, have actually been isolated and stored in bottles. 6 pi electron system. In benzene, 6 electrons are completely delocalized over all the 6 carbon atoms of the ring. Cyclopentadiene contains 4 pi electron and hence is not aromatic. However, cyclopentadienyl anion is aromatic because it contains delocalized 6 pi electron and is also planar. Cycloheptatriene contains 6 pi electron, but the electrons are delocalized over 6 carbon atom only and not over all the 7 carbon atom of the ring. Furthermore, it is not planar. Therefore, it is not aromatic but behaves like a typical alkene undergoing electrophilic addition reaction. Cycloheptatrinyl cation tropylumium ion, on the other hand, is planar and also has 6 pi electrons, which are completely delocalized over the entire cyclic system and hence is aromatic. Third, the polycyclic benzazonide compound and their derivative, in which one or more benzene rings are fused together, are also aromatic as shown below. Monocyclic heterocyclic compound containing one or more heteroatom are also having 6 pi electrons or aromatic sextet. Non-aromatic compound. These are closed chain compound which do not have conjugated double bond but follow Huckel rule, that is 4n plus 2 pi electron and flatness of structure. The stability of these compounds is comparable of that of corresponding acyclic compound. For example, cyclopropene, cycloheptatriene, annulyl 10 pi electrons, annuline 14 pi electron and non-planar. Anti-aromatic compound. The planar cyclic compound having completely conjugated at double bond and 4n pi electrons are called anti-aromatic compound. In these compounds, delocalization lead to destabilization and therefore these compounds are less stable than the corresponding cyclic compound containing conjugated double bond. Following are few examples of anti-aromatic compound: cyclobutadiene, cyclopropenyl anion, cyclopentadienyl cation, cyclopentadienyl anion. Thank you.